Good morning, everyone. Welcome back to another discussion in dynamics. Plan for today is following. We will start with a very brief lecture review. Professor Sunny started new topic yesterday. Yes, it was linear momentum of particles. And today we will just do 3 examples. I will try to do 3 examples with you, okay? Let's see where are we placed on our timeline. So we are done with kinematics, kinetics, and work energy, right? We start today new topic, 4th one, yeah. All right. Any questions? Example number 1. No, not example number 1. Brief lecture review. So. I would like you guys to just remember exactly the same thing that we're talking about so far, like 4 times. Yes, we have a particle P, and particle P is traveling along this trajectory, right? And there is that particle has mass, of course, and there is some net force acting on our particle. And before, when we were talking about the work energy method, I hope that you remember that we were integrating over path, right? And that's why we were using this definition of acceleration, yes? And we just projected our force and inertia force on the path, and after some algebraical transformations, we ended up with this well-known expression. Well known for you right now, I hope. When it comes to momentum, so topic of today, it's actually an integral of this equation, F equals to ma, but over time. Yep. That's why we will just introduce this definition of acceleration. Okay. So I will just plug if we plug this expression here, we will just end up with such expression. F dt is equal to m dv, right? And we will just integrate from time 0 to time final. Okay, the integral on the left is called, this is a definition of an impulse. And this integral on the right is naturally mv at time instant 2 minus mv at time instant 1. So let's just bring the term multiplied by -1 to the left-hand side, and we will end up with mv1 plus an impulse from t0 to t final and this is equal to our final momentum. Okay, so this is our momentum equation. We will use it today at least 3 times. Any questions? Yeah, in other words, initial momentum plus impulse acting on our particle will result in final momentum. Questions? I don't hear any. Example number 1 then. Please familiarize yourself briefly with the problem statement before we start our solution. Okay. And for those of you who are watching this on YouTube, you can pause the video and familiarize yourself with the problem statement. Okay, so what do we have in here? Aha, we have our particle, so our car, but we will model it as a particle, right? And that car, together with the driver, has some mass, and we know that it starts from velocity 0. Yes. Oh, sorry, not here. Velocity 0, and it needs only 4.2 seconds to reach 62 miles per hour. And we know that there is force coming from the engine, or the force propelling the car is given to us as such expression. Okay, and this is unknown, so they just ask us to find that f0 based on the rest of the information. Okay, so this is how I solve those problems. I just start with momentum diagrams. So I will just model our car as a particle, and I will just express it as a rectangle. And I will just draw what happens at time instant t0. Okay, so this is this drawing. In here we will have what happens in this time range from t0 to t final. And in here, we'll just see what happens at t final. Okay, so we'll just have three rectangles here. We have a rectangle here, we'll have a rectangle here, and we'll have exactly the same rectangle here. So I believe that our particle starts from rest, right? So we have mv0, and this is equal to 0, right? Then eventually, at the end, we will have some velocity, yeah? We'll have mv final. This will be our momentum. And in here, I just would like to draw all the forces that act on our particle. So I believe that we have mg, that actually in this case we don't care about. We have normal force. And also we have that force we care about. We have our f that is given to us as a function of time. Okay, so let's also not forget about our integral, because just remember from our previous board that initial momentum plus impulse dt is equal to final momentum. Okay, any questions to these momentum diagrams? Yeah, I'm just showing exactly what happens with the system in terms of moments and impulses, yes? So our next step will be momentum equation, yeah, or equations. Okay, of course, these equations will correspond to the diagram, yes? And we should just focus on momentum in the x direction. Okay, and this is our positive direction. Let's define this as our positive direction. And you can already see that our momentum is a vector quantity, yes? Energy was scalar. This guy can have x component, y component, depends, or any other component. You can write the momentum equation in any direction you want. However, when it comes to work energy, it was always a scalar equation. Okay, so what we had at the beginning, we had mv0 plus some integral from t0 to tf of f dt, and this will end up with mv final. Okay, let's plug in values. So I think that we started from 0. This integral will be from 0 to 4.2, f0 1 minus e to minus t divided by tau dt, and this is equal to mvf. Okay, this thingy is constant. This guy is constant. So let's just put it outside of our integral. Yeah, we can just place it in front of the integral. Okay, if I remember correctly from school, this will be equal to f0 times t plus tau e to minus t tau from 0 to 4.2. This is equal to mvf. And that integral will be f0 4.2 plus 0.5 e to minus 4.2 divided by 0.5 minus 0 minus 0.5. And this is equal to 3850 divided by 32.2 times 90.9333. All right. If you grab your calculators, you can figure out that this thing is approximately 3.700, and this thing is approximately 108.72.460, and triumphantly our f0 is approximately 2938.503 pounds. Answer. Questions? Hey, Hamilton, come on. I'm not that fast. You can take off the hoodie. You are caught in the middle. Come on. Okay, any questions? Yeah. So dedication. Wow. Okay, example number 2, or do you need a couple 10 more seconds for you? Okay, so example number 2. This one is interesting, actually. There's like 2 things that are very interesting. At least they are for me. Maybe not for you. We'll see. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, it's an interesting system, don't you think? I mean, we will see. So we have 2 masses this time, yes? We have big mass, ramp, yeah? And we have this box of different mass than the ramp. And what did they tell us? Aha, that system starts from rest, that this angle is 30 degrees, that there is no friction in the system also. This is important. And that information is given to us here. Ramp is smooth. Yeah, the surface of ramp is smooth. Okay, that means that there is no friction in the system. We will use this information within like 10 minutes or something. And they told us to find velocity of this big thing and velocity of this little thing when little thing covers 3.5 meters, yes, down the incline. Okay? Any questions to the problem statement? Yeah. So if not, we will just follow exactly the same steps. Okay, we will start with momentum diagrams. Okay. Momentum diagram. So I will for sure draw things that happened at time instant 0, time instant final, and time instant in between those two, yeah? So it will be, the first drawing will be for t equals to 0 or t0. I think we don't know how much that motion lasts, yeah? We don't have any information about time, yeah? Then I just would like to have something for t belonging to t0 to t final. And then here we will have t equals to t final, okay? So let's draw these situations. Let me put this ramp here. Here, here, and here. Okay, I think that our box will start its motion from here. Right? And this distance is 3.5. What else do we know? Aha, that at the end, our thing will be here, right? And in this time instant, I don't know, it will be somewhere here, whatever, somewhere in between. Great. So what do we know about our system at time instant 0? Aha, it does not move, yeah, it starts from rest. So you guys can just write that this is M, this is big M, and this guy has MV0, or maybe, let's do maybe MVC0, let's say. C for crate, okay? C, crate. And this one will be MVR0 is also 0. So R for ramp. Okay, system starts from rest. What do we know? What happens at the end? We know that this guy will move this way. Yep. M, it's big M, V ramp, yeah, yeah. And we know that this thing, we actually cannot guess the direction of the velocity for this thing, but we know that it will move together with the ramp, plus it will have a relative motion with respect to ramp, yes? So actually velocity of this guy will contain two components. It will be MVR and MV crate with respect to ramp. Yeah. So you guys can see that in fact our, you know how to add vectors, I have no doubts about it, yeah? In fact, our crate will have such velocity. This will be ND crate. Right? Do you see that? I hope you see that, guys. If not, you can ask questions, of course. Okay, so we are done with our momentums at the beginning, at the end. Let's focus on impulses. What forces act on our system? Okay, so for sure, big guy has mg acting downwards. Little guy has mg acting downwards. There are some internal forces between those bodies, yes? I'm not gonna show them, because we are focusing on the entire system, okay? We are not focusing on each body separately. These forces, there are some internal forces here between those two bodies, but there is one more force acting on the system. Normal force, yeah? Acting on the big ramp. Okay. Let's not forget about our integral. Great. We are done with our momentum diagram. Any questions? Yes, Jason?
Would it matter if there's two wheels without chains and no
You're right. You can, in the future, it might. Yes, you're right that actually there is like a normal force acting here and normal force acting here. So in this case, okay, you're right. Actually, it doesn't matter. If you want, you can put N1 and N2 in here, N1 and N2 in here. It won't change the solution at all. Okay? Do you mind if I stay with one N? Can we just forget about these wheels, guys? Yeah. The ramp is just sliding on the smooth surface. Okay? Good question. Thank you. Do you know that I actually didn't notice that? Yeah. I'm gonna stay with that. The solution will be exactly the same. You will see why in a second. Okay, but let's assume that there's only one. Any other questions? Yeah. Yeah. So let's assume that there is actually only one force N acting on our system. Okay. Do you guys? I have a question to you. Do you guys think it's a digression that this N is equal to mg plus mg? Yeah, if you look at that diagram, our system cannot move. Yeah, in the ramp cannot move in the vertical direction. Is this true? Okay, I see one no. I see two no's. Anybody thinks that it is true? Yeah, you think so? Yeah, don't worry. And why is it not true then? Why this is not true? Anybody can tell me? Yeah, go for it. Yeah, or wait a second, Jason, go for it. Yeah. Exactly. Little mass is accelerating. Yeah, sorry. Exactly. Yeah. This guy is accelerating. Yes. Downwards. Yes. If you solve that problem at home, if you use kinetics, you will end up. So this is not true. Yeah, but this is true. N is equal to mg plus m cosine squared theta m plus m sine squared theta. And I think I forgot G somewhere, yes? G should be here also, yes? G. Yeah, I have mistaken my notes. Yeah. But now I don't. I have new notes right now. Yeah? Just if you solve it at home, you will guys see that this is the correct expression for n. And just use your knowledge from kinetics. Alrighty, that's the end of the digression. Let's go back to our solution, okay? Momentum equations, yeah. So I just would like to ask you guys, do you see any force in this drawing acting in the x direction? Is there any force acting in the x direction? No. The only forces that act on our system are in the y direction, yes? And by the way, we do not want to calculate that n. We don't want to do it, yes? So if there are no forces acting in the x direction, what can we say about momentum in the x direction? It is preserved. It is preserved, exactly. So let's write that comment down, okay? No forces acting in the x direction. What implies momentum preserved in the x direction. maybe even momentum of the system, yeah? Of the system preserved in the x direction. Cool. So let's write in the x direction, and let's say that, I don't know, this is positive direction, let's say. Let's do it. So at the beginning we have mv crate 0 plus big M v ramp 0 plus our impulse plus 0, yeah? There's no impulse, yes? So plus 0, maybe, why do we write it? Let's erase it, yeah. And this is equal to minus mvr minus mvr plus, I must project this vector right now, yes? Okay, so let's project it on these two black directions. So if theta is here, I believe that theta will be here as well. So that would be, am I right? Theta here, yes. So that would be mv cr cosine theta, yes? Okay, so that would be plus mv cr cosine theta. All right. And these guys are 0, yeah? This is 0, and this is 0. So we ended up with 0 is equal to minus m vr minus m vr plus m vcr cosine theta. Okay, so how many equations do we have? 1. And how many unknowns do we have? I'm afraid that 2. This one and this one, yeah? Okay, not good. We have 1 equation, 1 unknown. We need another equation. Before we start finding it, questions? What happened so far? Yes. Thank you. It was a test for you. Yes. No, I'm kidding. I made a mistake. Thank you. Yeah. Some of you might wondering why we do not care about y direction. Yes. I think I already answered it. Yeah. Because we do not want to find that n. Force n is not known. Yeah. I don't want to find it, to be honest. I found it at home, but I don't want to find it with you right now because you will fall asleep. Okay. Okay, so but maybe some other idea how to find second equation. Anybody? Yeah. And your name must be Anna? No, okay. No, you're not Samantha because Samantha is not here today. Christina? So you can kill me right now. Okay, what's your name? Huh? Of course it's Erwin. Okay. Erwin, I'm sorry, what's your idea? Louder? Relation equations? You mean for this one? But relation for what? Here and here. I'm afraid that actually this might not be correct, but don't worry, because these are two independent variables. Yes, the relation is exactly here. So you can see that this is our relation. Yes, VR plus this is this. However, what is this? We don't know that either. Yeah. So okay, that's a idea, but it will not move us towards the solution. Okay. But there is Jason here sitting, and he has an idea. Jason, what's up? The displacement somehow I can use. I love those. I love those blur ideas. Like maybe we could do it somehow. I don't know. No, it's funny. I'm sorry. Yeah. Maybe. And your name is Isaac. Yes.
You can use the conservation
Exactly. And why I can do it?
because there's no like
Yeah, and no friction. Yeah, no dissipation in the energy. Yes. Okay. 3 times makes a charm. Yes. Okay. And there is no friction in the system. Exactly. We're gonna go for conservation of energy. Let's write it down. Okay. No dissipation in the system. Energy is preserved. Okay. So let's write our favorite equation, right? T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And Isaac said this is 0. This is what you said. Yeah, perfect. Okay. So let's find our 5 guys. Actually 4 in that case. Yeah. So Isaac already solved 20% of the problem. So I don't know, maybe I will find the rest. I don't know. So system starts from rest. It's 0. And at the end, we have a velocity, right? At the end, we have 1/2 big M VR squared plus 1/2 little m VC squared. So actually, Erin was right, partially, because we are going to use Erin's idea. I'm going to use your idea in a second. Yeah, because you can clearly see that I introduced exactly what we were talking about earlier. Yeah. How about potential energies? Aha, we need a datum. Let me scroll up the board, okay? So I want to put my datum here. Okay, this is our datum. Datum. Okay, so at the end, our energy is 0. Yeah, because the only body that changes elevation is little body. So this will be 0. But that little body is above our datum at the beginning, yeah? And this distance will be as sine theta again. Yeah, okay. So this is our potential energy at the beginning. So that would be little m g s times sine theta. Okay, plug everything back into our equation, and we'll end up with something like that. mgs times sine theta. This is equal to 1/2 mvr squared plus 1/2 mvc squared. Okay, so we have another equation, but we introduced another unknown, yes? So we found our equation, but this guy is not known again. So still not solvable, okay? But we're gonna use do what Erin said earlier. We're gonna use this. So do you remember law of cosines? Yeah, this is, yes, law of cosines, yes? I hope that this is correct term in English. Now I'm not sure, but it is correct in English, yes? Law of cosines. Okay, thank you. So I believe that where is 30 degrees? We must bring 30 degrees in here somehow. Where is 30 degrees in here? I think it's here, yeah, because so 30 degrees will be here. Yeah, so it also will be here. Okay, so if I remember correctly from school, law of cosines is following. VC squared is equal to VR squared. So in that case, let's get rid of these m's, okay? We don't need m's in here. M. Plus VC relative to R squared minus 2 VR VC with respect to R cosine 30 degrees. So we found that relation, exactly, yeah. I don't know why I said no earlier. Now, plug back in here, plug this back in here, and we will end up with 2 equations and 2 unknowns. Any questions? So I'm gonna take this guy here. I'm gonna take this guy here. However, I'm going to replace this thing. I'm going to replace this thing with this. Great. We have 2 equations and 2 unknowns, which are VR and VCR. Okay, solve it at home. It's solvable. It's solvable, okay? We are going to just plug in values. And solve for VR, VC with respect to R. And once we have those 2, we can also find VC. Yeah. Clara? Yeah. We did it, but there are vectors, yes? So you mean add them vector-wise? The question is, do we know? My answer is no, because do you know why? Because we must first of all find a solution that is accurate from the physical standpoint. Okay, so look, we can add them once we know them. Okay, yeah, we can add VR and VCR once we know them. However, first we must find them. Okay, and in order to find them, we must go for conservation of momentum in the x direction only and conservation of energy. Okay, then we will have these 2 components, and then we can add them vector-wise. Okay. Okay, so I solved it yesterday at home. Actually, I solved it 1 year ago, but just for the heck of it, I'm just gonna say yesterday. So this is 1.004 meters per second, 6.353 meters per second, and this one will be 5.428 meters per second. Okay, and let's do what Clara said. So Clara said that we should add them. So I'm going to copy this drawing, and let's see if this makes sense. If this makes sense. So I said that this blue guy is 1.004. This red guy is 5.428. Yes, that makes sense for sure, because they must be the longest. This vector must be the longest. 6.353. Okay. And this is our answer, yes? This is our answer. This and this. answer. Clara, are we good? Yeah? Yeah. Do you see why I answered your question that in that way? Yeah. We can add them, but at the very end. Yeah. Questions? Other questions? How do you like that problem? It's interesting, yeah. Looks like exam problem for me. No, I'm kidding. Yeah. Yeah. So conservation of momentum and conservation of energy might be quite common here. Okay. So even though we are solely in conservation of or in momentum chapter, we still might use some help of the previous things. Okay. Example number 3. Let's do it. And please read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have again 2 bodies, I think, yes? And this is how it starts. We have big body here. We have small body here. We know the height, the initial height the big body was placed at. And we know that this ramp is smooth. There is no friction here. And system starts from rest. And they ask us to find 2 things, yes? They ask us to determine the speed of these 2 things once this guy is here and it just ends up on the cart. They told us to find the final velocity of these 2 things, right? This is part A, and part B they told us to do something when there is like a rope in here. Okay, they told us that then we should, in part B, we should like imagine that there is a rope in here, and they ask us to find tension in that rope, yeah, or like impulse in that rope. Okay, but before we go to part number A and part number B, we must solve work energy method. Yes, we must figure out what velocity this guy will have before entering the cart. Yes, so let's do it very quickly. Let's do drawing for config, or maybe let's not do. It's like too simple, yeah. So let's do T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And let's find these 5 guys. T1, V1, T2, V2, U12 non-conservative. Okay, guys. Anybody want to do it quickly? T1? 0. Okay, T2? The thing will be here. The thing will be here and it will have velocity. Yeah, so it would be 1/2 big M V star, let's say V star squared. That would be V star. Okay, let's say that our datum is here. Okay, so potential energy at the end will be 0. Potential energy at the beginning will be mg15. And this will be 0 because there's no friction. Okay. So we will end up with mgh equal to 1/2 mv star squared. That means that v star is 2gh. And that means that v star is square root of 966. And this is approximately 31.0805 feet per second. Great. So now we can go to part 2, point A of our problem. So I will start with momentum diagrams again. Okay, momentum diagram. All right, okay, so we will just do instant T0 with, so it will be pre-impact. I would like to also see what happens during the impact. And I would also like to know what happens after the impact, post-impact. Okay, so at the beginning we will have our card. And our particle will be here. Yeah. At the end, this die will have small m Vm0, and this is equal to 0. And this die will have big M V star, right? So I'm just going to copy this card here and here. And at the end, our particle will be somewhere here. I don't know, somewhere, let's say somewhere here maybe. Okay, and these two guys will have the same velocity. We'll have big M V final and small m V final. And in between the impact, these die will be like somewhere here, and we only have internal forces acting on our system. Internal forces. Yeah. That matter. Yeah. Because we also have like mg and stuff, but we just care about x direction. Yeah. So if you want, guys, you can write in here that it's mg, mg, and n. Oh. Uh-oh. And n. Yeah. So you again can see that these three guys act only in the vertical direction. Yes. So that means that our momentum in the x direction is preserved. Internal. And of course, let's not forget about our integral. So it will be from 0 to 0. Okay. So now momentum equation. In the x direction only, in the x. And positive direction, let's say this one. Why not? So at the end, at the beginning, we have mv star. And this will be equal to m plus m v final. Yep. So our v final is just m plus m v star. Plug in values, and this is approximately 20.721 feet per second. Okay. And it's 10:45. So I will try to finish this part with my other discussion, okay? And I will send you an email with the link, okay? Any questions? All right. See you guys. See you Friday.